The other type of series we're really interested in are these ones, the geometric series. Very similar definition, the only difference being we now multiply by a constant amount rather than adding a constant amount. So instead of having a common difference, we now have a common ratio. So symbolised R. So if I want to find that ratio, I could get the second term divided by the first term, or the third term divided by the second term. Or if I want a formula, again, I could get any term divided by the previous term. That would tell me what the common ratio is. Now a recursive formula, therefore, it would be, if I want to get term n, I'll get term n minus 1, multiply it by the common ratio. There's our recursive formula. So let's create a general formula then. First term is A. The recursive formula tells me I will multiply that by R. So second term, AR. Get the third term, multiply that by R, AR squared, and the pattern starts emerging. General term must be AR to the power of n minus 1. So the power will be 1 less than the number of terms. This time, if we were to plot it on our number plane, we would see an exponential function. It's just like exponential functions where, let's say it was y equals 2 to the power of x, the x is in the power. Well, that's where the n is in our one. So it's just like an exponential function. If you would plot it, we would see an exponential graph. Here's our pattern, 2, 8, 32. What's the ratio? And then work out the general term. A is 2. I've multiplied by 4. We should really check and make sure. And 8 4s are 32 as well. So yes, it is a regular pattern, just to make sure. But the fact that they've asked me to find the general term sort of implies that, yeah, it's going to be a regular pattern. For term n, AR to the n minus 1, that'll be 2 times 4 to the power of n minus 1. In this case, I can do better than that, because I could rewrite 4 as 2 squared. And then using index laws, we get that's 2 to the power of 2n minus 2. I can even go further with that one, and I just end up with 2 to the power of 2n minus 1 for a general term. Now that won't always work, of course. If I had a common ratio there that was, say, 3, well, I couldn't have done that, because I couldn't have said 2 to the power of something times 3 to the power of something. It doesn't work. Our second term is 7, our fourth term is 49. What is the general term? Got to work out what the first term is, got to work out what the common ratio is. The second term is 7, so AR is equal to 7, and AR cubed is 49. They are simultaneous equations, but instead of subtracting or adding, what I'm going to do here is divide. If I was to divide, then the A will eliminate. So R squared, I'm dividing the bottom one by the top one here. R squared would be 49 divided by 7. R squared is 7. But that brings up an interesting problem. Is the ratio plus the square root of 7 or minus the square root of 7? Because that's the thing with a geometric one. The pattern could go plus minus, plus minus, plus minus, plus minus. You've still got a common ratio, it's just that it's a negative number. Well, I can't tell unless they give me more information. Let's substitute back in and work out A, and that will depend on the ratio. Now, if the ratio was positive, then A must have been positive, so it'll be positive square root of 7. If the ratio is negative, then the first term must have been negative to get that pattern right. I'm just going to write it with the positive one and say, well, it's root 7 times root 7 to the n minus 1. The other possibility could have been this. Minus root 7 times minus root 7, it gives me minus root 7 to the power of n. When you see something like that, we usually pull the negative 1 out and write it by itself, because that's the thing that's controlling whether the number's positive or negative. It's that negative 1. Is it to an odd power or an even power? And that'll tell you whether a number's positive or negative. So we tend to pull the negative 1 out on something like that. So what would the first term of this pattern be greater than 500? Which one? Okay, first term is 1, the ratio is 4. So my general term, 1 times 4 to the n minus 1. Well, 1 times anything is that thing, so I could just write that as 4 to the n minus 1. I want to know when that term's greater than 500. So when is 4 to the power of n minus 1 greater than 500? Now, we could do it by trial and error. That's certainly a method. And as we're dealing with whole numbers, okay, that could work. But let's use logs. That's a more efficient way of doing it. Log both sides. That allows me to bring the power to the front. I'll now divide both sides by log 4. Log 4 is a positive number. If it was a log of a number smaller than 1, that's actually a negative number, so be careful with inequalities. So n minus 1 is greater than, and that works out to be about 4.48. Add 1. We want the first integer bigger than that, so 6. So term 6, which would be 1024. That would be the first one bigger than 500. We'll talk a bit about this thing called arithmetic and geometric means. Now you've already seen it, but you've seen arithmetic mean. It's what you understand average to be, and that's why sometimes it's called mean, because it's actually the arithmetic mean. So arithmetic mean is the same as average. In other words, you just add them all up and divide by the number of terms you got. That's what an arithmetic mean is. Geometric mean is slightly different, because instead of adding, we multiply. So we multiply them all together, but then we find the nth root. So if you've got 2 terms, you'd find the square root. If you've got 3 terms, you find the cube root, and so on. Technically, it's plus or minus. We tend to go with the plus. But again, it could be an alternating pattern, so you could get plus or minus. So if I've got 4 and 25, 2 numbers, what would the difference between these two things be? The arithmetic mean, add them together, divide by 2, I get 29 on 2. Geometric, multiply them together, I get 100, square root of 100 is 10, so plus or minus 10. What you're actually doing when you're finding a mean between two numbers is place a number in the middle to create, in the first one, an arithmetic pattern, and in the second one, that would create a geometric pattern. So if you went 4, 10, 25, that would be a geometric pattern. So that's what these means do. So having said that, if this forms a GP, so geometric progression or pattern, we've got to find x and y. So we're going 2, then x, y, and 128. We're going to get a geometric one. Now it's easier to do them in pairs, so find the ones in the middle. So what would be in the middle of 2 and y? Well, it would be the square root of 2y. Multiply them together, find the square root. And then I could get x and 128. What would be in between those? Well, y would be the square root of 128x. Again, I've got simultaneous equations. Y squared, if I square that, I'll get 128x. Substitute the x in. I now know y squared is 128 times the square root of 2y. I'll get rid of the square root, so I'm by squaring again. I've got y to the power of 4 is equal to 32,768. Y, we have this to solve. 2 possibilities. One is y equals 0. That's a bit strange. The other one's y equals 32. So you go back to your pattern and think, well, does this make sense? Because if that's y, well, 0 can't be in a geometric progression, because remember, how do we get the numbers? We multiply by a common ratio. So as soon as you get 0, if you multiply, you're going to get 0. 0. And every term after that must be 0. Well, that's not true, because we've got 128. And actually, if you think about it, every number before must have been 0 as well, because how did you get the 0? You've multiplied by something to get 0. So 0 is not going to be a possibility. Must have been 32. Subbing back in, that gives us that x is 8, and we've got our pattern. It would go 2, 8, 32, 128. That would be a geometric. There we go. So we'll add those ones in.